The atom. The atom is one of the most fundamental concepts that we study in chemistry, but it's also one of the most important. The reason is understanding what an atom is and how it behaves will allow us to understand all of the matter that makes up the universe around us. All of that matter is made up of very tiny pieces, and one type of those pieces are what are called atoms. When we say very tiny, it can be hard to visualize what exactly that means. Fortunately, there's a good resource to help us do that. What you're looking at right now is an interactive diagram that's going to help us to understand exactly how small an atom actually is. This diagram was produced by the genetics department at the University of Utah, and if you'd like to come back and explore it a little more on your own, notice that its website is at the top of the screen. We're starting by looking at some things that we would probably describe to be small objects, but that most people can probably still see with the naked eye. Things like a coffee bean or a grain of rice, and here's 12-point font when printed on paper. All of these things could be measured in terms of millimeters. Remember that a millimeter is 1/1000th of a meter. Now I'm going to start to zoom in to some even smaller objects. When I get down to about a 1/2 millimeter, that's approximately the size of a grain of salt. Again, something that some people can see with the naked eye. Other people are going to start to need help, like magnification or maybe a microscope. As I zoom in further, I reach the level where I see things like an amoeba or a paramecium. Now we're measuring in terms of micrometers, which is to say a billionth, or rather a millionth of a meter. As I zoom in further, I'll see different types of cells, and I can continue to zoom in till I get down to bacteria. Notice that now we're measuring in a fraction of a micrometer, and yet we're still dealing with things that are millions and billions of times larger than the atom. So let's continue zooming in. Past the bacteria, I start to encounter viruses. Most viruses are measured on the order of magnitude of nanometers. So the flu virus, or HIV, these are measured in nanometers, or approximately a billionth of a meter. But I continue to zoom in because I still haven't reached the point of being able to see the atom. I move past things you might remember from a biology class before, and I finally start to get down to the level of things that have individual atoms, or an individual atom itself. Here is a carbon atom, which is a fairly typical atom on the periodic table. It's about 340 picometers across. Pico means billionth, so 340 billionths of a meter. Now that we've seen how small an atom really is, let's zoom out to have some appreciation for the fact that all the matter around us is made of these little tiny pieces. Having looked at that interactive diagram, now you have a real appreciation for just how small these things called atoms actually are. And keep in mind, atoms make up 100% of all of the matter in the entire universe. So everything around you is made up entirely of atoms. Those atoms can combine together to make more complex structures, things like molecules or cells, and the cells can come together to make things like living beings, like you. Chemists are generally interested with the smallest pieces of matter, and that doesn't matter whether we're studying something very large or something very small. If you think about something like an apple, now you can appreciate that if we were to look at it on a very, very small scale, it actually becomes really complex and really interesting. Even though there's a lot of levels of complexity, chemists are generally interested in the two simplest pieces of matter that make up everything around us. The simplest, by far, is the atom. If we could zoom in on that apple the same way we did in that interactive diagram, we could see that it's made up of individual atoms. We say that atoms are the smallest and simplest piece of matter that still retains everything that makes that matter what it is. Here's another way to understand that. If you took an apple and you split it in half, you'd have two pieces of an apple. Well, if you take an atom and you split it in half, you have two pieces of something, but they're no longer whatever type of matter you were dealing with before. So it's the smallest and simplest piece of matter that still retains the qualities of that matter. You can split an atom and you can come up with what it's made of, but that's really something that we only look at in a little bit of detail during this course. The other type of piece of matter that chemists are interested in are what are called molecules. And we'll see a lot of times when you study the human body, you're not as interested in the atoms as what they come together to make, which are molecules. Molecules are what we call collections of atoms that have been connected together. So anytime you bond two or more atoms to each other, and that's something we'll look at in a lot more detail this quarter, you have what's called a molecule. In an apple, if you really could zoom in on it and see all the way down to that atomic level, you would see individual atoms, atoms like sodium and potassium. But you'd also see a lot of molecules, molecules like fructose or fruit sugar. So these two types of matter, atoms and molecules, are really building blocks for everything else that's around us in the world. Even though atoms are incredibly small, they're actually fairly interesting. To begin with, there are more than 100 different types of atoms. Currently, scientists have counted 118 different types of atoms, and we know that at least theoretically, there are more out there. These different types of atoms are what we call elements. So when someone says the word element, they just mean one particular type of atom. We can put all of the known elements together on the periodic table of the elements, and we'll be studying the periodic table in a lot of detail shortly. For now, realize that you probably already know many of the elements on the periodic table. For instance, elements like silver, gold, copper, and sodium. There's probably plenty of elements you don't know on the periodic table as well. For instance, have you ever heard of praseodymium or seborgium? It's interesting to consider that while all the matter in the universe is made up of atoms, it's the exact combinations of this matter that the exact combination of these atoms that give matter its unique properties. For instance, if you'd like to make water, you need to put together two atoms of the element hydrogen with one atom of the element oxygen. That's the only combination that will make water. To make something like the human body, you need billions and billions and billions of different atoms from many different elements. Let's look in more detail at the atom itself. If all the matter in the universe is constructed of these atoms, then it's a funny question to ask, what is the atom itself constructed of? I love this question because it has a fairly surprising answer, and that answer is mostly nothing at all. In fact, if you were to consider an atom as being like a sphere or an orb, about 99% of that orb would be empty space. And yet, from this empty space comes all the different matter in the universe. Let's look in more detail about the space as well as what's within it. Because the space plays such an important role in the universe, as well as understanding the atom itself, we usually divide the space within an atom into two distinct entities. One is called the nucleus, and the rest is called the orbitals. If you've taken a biology class, you probably guessed that the nucleus is the term we use for the center of the atom. It's important to realize, though, there's not a distinct boundary, like a membrane or a border, that defines the nucleus. It's simply a term we use to describe the center of the atom. Outside of the nucleus is the space referred to as the orbitals. And this term was originally coined because people believed that if something's in the center of the atom, anything outside of the center would orbit around that nucleus. In addition to all the empty space, there are three subatomic particles that put together make up the atom. The term subatomic means smaller than the atom, and these three subatomic particles are, of course, smaller than the atom itself. They include the proton, the neutron, and the electron. Each of these subatomic particles brings with it unique characteristics and helps to influence which type of atom we're dealing with. Let's look at them in more detail. Depending on the type of chemistry you're interested in, many scientists believe that the most interesting subatomic particle would have to be the proton, and we'll see why in a second. I'm going to show protons as being the letter P in a red circle. These protons are found in the nucleus of an atom, and every single atom has at least one proton in its nucleus. In fact, the smallest atom has exactly one proton there. Most of the other elements on the periodic table have dozens of protons, up to 118 of them. The mass of a proton, as you can imagine, is extremely small because we're talking about an object that's smaller than the atom itself. It wouldn't really be appropriate to talk about its size in terms of inches or pounds, so we use a unit of mass called the atomic mass unit, or the AMU. A proton has a mass of 1.007 AMU, or approximately 1 atomic mass unit. Protons are positively charged. That means for every proton in the atom has 1 positive charge, although we'll see that other subatomic particles can counteract this charge. Finally, let's look at why protons matter and why, as I said before, some chemists might argue they're the most important of the subatomic particle. The number of protons that are in each atom actually tells us which element that atom will be. In other words, the number of protons gives us the identity of the atom. The number of protons for this reason is often referred to as the atomic number of the atom, and it's something that can be easily found by looking on the periodic table. The atomic number is exactly equal to the number of protons that an atom of an element will have, and vice versa. So while we haven't looked at the periodic table yet, I can show you that it's a fairly easy number to find when you look at it. I'm going to zoom in on the top part of the periodic table just to make things easy to see. Looking at the first 3 rows of the periodic table, let's start in the upper left-hand corner with the element hydrogen. Whether you look at the periodic table on the screen or a different version that you may have with you at home, you'll notice that the element hydrogen has a large number 1 written in the box above its symbol. This number 1 is the atomic number, and it indicates that all atoms of hydrogen have exactly 1 proton in each nucleus. So a hydrogen will always have 1 proton, and therefore its atomic number is 1. If we move on to the second element on the periodic table, which has an atomic number of 2, this is helium. This means that all helium atoms have exactly 2 protons in their nuclei. This pattern continues on the second row of the periodic table. Lithium has 3 protons in its nucleus, or an atomic number of 3. Beryllium has 4. Boron has an atomic number of 5, and 5 protons in its nucleus. And so this pattern continues. Let's see if you can use this information to find out something about the periodic table. If I'm working with an atom that has 16 protons, what element am I working with? Well, looking at your periodic table or the one on the screen, you simply need to find the square that has the large number 16 in it. In this case, it's sulfur. So the answer to this question is, if I'm working with an atom that has 16 protons, it must be the element sulfur. Let's look at another subatomic particle called the neutron. I'm going to represent a neutron on our little diagram as an N in a green circle. The neutron is similar to the proton in 2 ways. First of all, like protons, neutrons are found in the nucleus of an atom. Also like protons, their mass is roughly 1 AMU. You might remember that protons had a mass of 1.007 AMU, while neutrons have a mass of 1.009 AMU. So to summarize, both protons and neutrons are found in the nucleus of an atom and have a mass of approximately 1 AMU. This is where the similarities end. Neutrons get their name from the fact that they're neutral, or in other words, they have no charge, positive or negative. So why are neutrons important? Well, protons are important because they help dictate which element an atom actually is. Neutrons are important because they dictate the stability of that atom. And stability, in turn, is related to the issue of radioactivity. So the number of neutrons in the nucleus of an atom influences whether that atom is radioactive or not. We'll cover radioactivity in detail later in this quarter, but let's just look briefly at why this matters. Some atoms are radioactive, meaning that over time, if left alone, they begin to fall apart. In other words, they're unstable.
We call this process decay. And when an atom decays or falls apart, it can release things like very, very small pieces of itself or energy. And anything around it, especially living things, can be impacted by this decay. This is why people like to avoid being around radioactive material. Essentially, when you avoid radioactive material, you're avoiding the decay of atoms, which can release damaging energy and particles. It's important to realize, though, that just the element itself doesn't dictate whether you're dealing with a radioactive atom or not. For instance, uranium, which many people think of in relation to nuclear power and radioactivity, uranium has atoms in the universe of uranium that are stable and other atoms which are radioactive. So for every element on the periodic table, there are some atoms of that element that are stable while other atoms are radioactive. Let's look at a much more common example, which is carbon. Carbon is located in the upper right-hand corner of your periodic table. It has the chemical symbol C. If you look at carbon, you'll notice its atomic number is 6, which means that all carbon atoms have 6 protons in their nucleus. That's a guarantee because that's what's defined by their atomic number. The number of neutrons, on the other hand, can vary between different carbon atoms. We usually expect that the number of neutrons will be the same or close to the number of protons. For instance, with carbon, some atoms of carbon have 6 neutrons, while other atoms of carbon have 8 neutrons. We say that these two different versions of carbon are isotopes of carbon. In other words, they're atoms that have the same number of protons, but the number of neutrons is different. The carbon atom on the left would have a mass of approximately 12 AMU, because we know that both protons and neutrons weigh approximately 1 AMU apiece. So adding up 6 protons and 6 neutrons, I've discovered that this carbon has a mass of 12 AMU. And in turn, I would refer to this as carbon 12. On the other hand, the carbon on the right side of the screen would have a mass of 14 AMU, because it has 6 protons and 8 neutrons. This number is referred to as the mass number, and it's what you'll recognize when we talk about radioactivity of different substances. The carbon on the left would be referred to as carbon 12. The carbon on the right would be referred to as carbon 14. This is where we get the numbers for things like uranium-235 or sodium-24.
Sometimes you'll see isotope symbols written instead of writing out the words carbon-12 or carbon-14. Isotope symbols always contain 2 parts, and sometimes you'll run into a third part, which is considered to be optional. In the large box, we fill in the chemical symbol. If we're doing the isotope symbol for carbon-14, we'd fill in a C for carbon. The 14, the mass number of that particular isotope, goes in the box on the upper left. The box that's considered to be optional is the box on the lower left. Sometimes people will include this information, and it's the information of the atomic number. For carbon, carbon's atomic number is 6. This is a little bit redundant because as long as you know that the element is carbon, there's no reason to include the atomic number. In print, the way this would appear is most commonly C14 or carbon-14. And again, you'll see any number of different isotopes. For carbon, you might also see carbon-12 or even carbon-13. And for any other element on the periodic table, other isotopes will always exist as well.
The mass number is simply the number of protons and neutrons added together, and it's how we usually recognize different radioactive elements. For example, the uranium that is radioactive and is used in things like nuclear power plants is uranium-235, while there's also radioactive uranium found in nature called uranium-238. It's important to realize that this number is not found on the periodic table. All that you'll find about carbon by looking there is its atomic number, which is its number of protons. You won't find any information about its mass number. Let's move on to our final subatomic particle, which is called the electron. I'm going to represent electrons as a little blue dot. Electrons are the only subatomic particle that's not found in the nucleus of an atom. And electrons basically are very, very, very small. Even when we measure them in atomic mass units, we're talking about something that is less than 1/1000th of an AMU. The other thing about electrons is that they move very, very quickly. And this again is how many people originally thought the atom might be set up, is that the electrons orbit around the nucleus. That's where we get the term orbitals from. Electrons all have a charge of -1. This means that they counteract the positive charges of the proton in the nucleus. And in fact, that means in order to have a neutral atom, you have to have exactly as many protons as electrons. So why do electrons matter? Well, the charge is actually the reason that they matter. Because electrons are in the orbitals, which are the outer reaches of the atom, they can be gained and lost. And when that happens, you can have an inequality in the number of protons and the number of electrons. So the number of electrons will end up dictating your charge, whether it's neutral, whether your atom becomes positively charged, or whether your atom becomes negatively charged. These are what we refer to as ions or electrolytes. Ions are atoms that have either a positive or negative charge, and they get that by having an imbalance in the number of protons and electrons. So, to review, there's 3 subatomic particles. In the nucleus, we have the protons and neutrons, which both weigh about 1 AMU, and orbiting around the nucleus are the electrons, which are much smaller in comparison. The rest of the atom is mostly empty space. These 3 subatomic particles put together in different combinations give us enough variety to create all of the different elements, all 118 of them, on the periodic table. Let's look in more detail about the periodic table now. This is the periodic table of the elements, better known as the periodic table. While as a chemist I'm a little bit biased, I have to tell you that I think the periodic table is really interesting. And not just because there's a lot of stuff on it. The periodic table is a fascinating way of displaying all the elements in the universe in a way that gives us, almost secretly, information about each one. If you know how to read the periodic table correctly, you can basically make conclusions about substances you've never seen or heard of before in your life. In fact, some people consider it to be the ultimate cheat sheet. And I can tell you from experience, the deeper you go into chemistry, the more ways you discover how right the periodic table is. It wasn't always this way. 200 years ago, when scientists were just starting to discover concepts like atoms and elements, there was a lot of discussion about how they should arrange these newfound substances. Some people wanted to put them in lists, and other people wanted to put them in tables. There were lots of different proposals. But the periodic table that we look at today was largely formalized by Dmitri Mendeleev in a paper he published in 1869. What Dmitri did that was different from other scientists is when he laid out his chart, the periodic table as we know it, he noticed that when you put together all the different substances we were aware of, there were some holes. Basically, there were places where he would expect an element to exist that hadn't been discovered yet. In fact, this is exactly what happened. After Dmitri Mendeleev proposed this paper, later on scientists discovered elements that he had simply hypothesized about their existence. So for this reason, we largely give Dmitri Mendeleev credit for the current periodic table. The table is periodic, just like a calendar is periodic. A calendar goes through periods of weeks, while the periodic table moves through different types of elements. If you look at it this way, you can already see how the periodic table gives you information. For instance, on a calendar, you might say the first day of the week that would be displayed is Monday. If we go to the first column on the periodic table, this is equivalent to saying the first column of Mondays. And just like every Monday you have a similar schedule with small variations, All of the elements in this first column will be chemically similar to each other. So in this way, the periodic table notices and uses and takes advantage of similarities and periodic trends in the elements. If we look in more detail at the individual boxes that make up the periodic table, there's a lot of variety, not just on this table, but between different tables themselves. Let me show you how to spot the most important pieces of information, regardless of what periodic table you're actually working with. We've already talked about the atomic number that's located somewhere in that box for every element. The atomic number, or the number of protons, increases starting with 1 in the upper left-hand corner of the table with hydrogen and moving down through 100, 110, or 118, depending on how modern and up-to-date your periodic table is. You'll also notice that in each box there's a chemical symbol. The symbol is represented by either 1 or 2 letters, and it's important to realize that the first letter is always uppercase. If there is a second letter, it will always be lowercase. The reason this is important is it'll allow us to string together chemical symbols in something called a formula and know where one symbol starts and the other one ends. A good example of why this is important is if you were to write C and O next to each other. If you write a C and a capital O next to each other, you're actually writing a carbon atom and an oxygen atom, which is a compound called carbon monoxide. Whereas if you write a capital C and a lowercase o next to each other, you're writing the symbol for the element cobalt, a very different substance. So it's important to be sure that it's very easy to read your writing and that there's always uppercase and then lowercase letters. The other number that's located on most periodic tables is what's called the atomic mass, or the atomic weight. It's important to realize that this is different than the mass number, which we talked about in relation to isotopes. The weight is related to these isotopes, but the difference is we know that different isotopes exist for each element on the periodic table. For example, with carbon, we've already discussed that carbon has an isotope called carbon-12 as well as an isotope called carbon-14. The atomic weight, on the other hand, is an average of those isotopes. The weight is given in units of AMU, so in this case, this means that all carbon atoms in the universe, if you added them all up and averaged their weight, they'd have an average weight of 12.011 AMU. What that means on a less tangible level is that really the most common isotope of carbon is probably carbon-12 because the weight is so close to that isotope value. If you look around your periodic table, you'll notice many of the atomic weights are very close to a whole number. Sometimes they're numbers like 17.99 or 18.01. That's because usually one isotope is much more common.
With so many different elements on this huge periodic table, it's important to know that there's different ways you can navigate the periodic table, meaning there's ways you can break it apart into more usable pieces. One of the easiest ways is to divide it into elements that are called metals and nonmetals. The metals on the periodic table are shown in yellow on this particular version, and the metals, you'll notice, make up about 2/3 of the table. They're located predominantly on the left side of the table, and in fact the only element on the left side that's not a metal is hydrogen. Metals have certain physical and chemical characteristics in common with each other. When you picture metal, you're probably picturing some of these particular properties. For instance, metals are usually shiny. That means they have luster or they reflect light. Metals are also malleable. That literally means if you hit them with a mallet, it'll leave an indentation. So they can be formed into different shapes. Sometimes this is also referred to as being ductile because metals can be formed into ducts, wires, and so on. Metals have the property of being conductive, and they conduct both heat and electricity. This is one reason that you use metal cookware. The metal cookware allows the heat from your heating element or fire to be conducted through the pan into your food. And finally, most metals are solid at room temperature. There's only one exception to this rule, and that's mercury. Mercury is a metal that's actually liquid at room temperature, but it's still shiny, malleable, and conductive. On the other side of the periodic table, you'll see the elements that are considered to be nonmetals. These elements are colored blue on this particular version. In addition to the elements on the upper right-hand side of the periodic table, hydrogen is also considered to be a nonmetal. Nonmetals have chemical and physical properties that are the opposite of metals. So whereas metals were shiny and reflect light, nonmetals tend to be dull. Nonmetals are often brittle. That means if you strike them with a mallet, instead of leaving an indentation, they'll shatter. Nonmetals are also insulating to heat and to electricity. This is why we use the different elements that are nonmetals if we want to insulate something. For instance, with double-paned windows, you might use oxygen gas, nitrogen gas, or argon gas. Finally, the nonmetals range in which physical state they occupy at room temperature. Many of them are liquids or gases. Some of them are also solids. You'll notice that in between the metals and nonmetals, there's a little zigzag line of elements that are colored green on this table. These are what are referred to as the metalloid elements. Metalloids, much like anything that exists on a border between two different areas, have qualities and properties from each side of their line. That means that they take on some properties of metals and some properties of nonmetals. A good example is silicon. Silicon, which has been made famous by silicon computer chips in Silicon Valley, is able to conduct electricity very well. That's a metal-like property. Silicon, on the other hand, is very brittle, which is a non-metal-like property. So the metalloids have different properties depending on which element we're speaking of, but they tend to combine properties from both the metal and non-metal side of the periodic table. In addition to dividing the periodic table into these large sections called metals and nonmetals, we can also speak about more specific areas. One way the periodic table is often divided is into periods and groups. Periods, which really just means rows, are the rows that move across the periodic table. And they get their name from the fact that the periodic table, like a calendar, is regular and repeating. So a calendar would have a period of a week that moves across one row. We use the same type of terminology here on the periodic table. So period 1 on the periodic table is like the first week on a calendar. In this case, period 1 includes just two elements, hydrogen and helium. Period 2 is the second row on the periodic table. It includes lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. And in this way, we can continue down the remaining periods. Period 3 is really the third period of the periodic table, with sodium, magnesium, aluminum, and so on. Period 4 is the fourth row of the periodic table. Period 5 is the fifth row, and period 6 and 7 are the last two rows. Something interesting, though, happens at period 6 and 7. Notice that period 6 extends not just across the periodic table, but also across the separate group of elements shown at the bottom of this slide. This is what's called the lanthanide series of elements. And there's nothing actually that surprising going on here. You'll notice the lanthanide series starts with cerium, atomic number 58, and goes through atomic number 71. What really is happening is those elements should appear between lanthanum, number 57 on the periodic table, and hafnium, number 72. Why are they not displayed there? Well, it's a practical matter. If we put all of those elements in that space, the periodic table would be so wide it would never fit on a slide, a handout, or a textbook page. So for that reason, we simply move that section of elements down to the row below the periodic table. They're still considered to be part of period 6. The same is true for period 7, which has the actinide series removed from after atomic number 89. It includes elements number 90 through 103, but it's simply part of period 7. In addition to the periods on the periodic table, there are also the columns, which are referred to as groups. There are a total of 8 groups that are customarily discussed on the periodic table, beginning with the very first column on the periodic table and then moving across. Group 1 on the periodic table starts with hydrogen and includes lithium, sodium, potassium, and so on. Sometimes you'll hear hydrogen omitted from discussions about Group 1, and the reason for that is that hydrogen's a nonmetal, so it doesn't really belong in Group 1 from a chemical standpoint. Why is it there? Well, in order to maintain some other types of symmetry on the periodic table, which we'll discuss later, it's still convenient to keep it in that first position. So Group 1 is the first group or first column on the table, followed by Group 2, which starts with beryllium, includes magnesium, and so on. In the middle of the periodic table, we customarily don't number this middle section in terms of groups, but rather we refer to this entire little valley as the transition metals. These are metals that can be grouped together because they're very similar chemically. They do have some unique and interesting chemistry within the group, but much of it is beyond the realm of general chemistry, so we'll simply refer to these as the transition metals. The group numbering picks up on the other side of the transition metals with Group 3 that starts with boron, includes aluminum, gallium, and so on. Group 4 starts with carbon, 5 is nitrogen, and all the way across over to helium in Group 8. What's interesting about the groups is that the elements within any given group are very similar to each other in terms of chemical reactivity. In fact, some of them are so similar that they've been given special names. Group 1 is a good example. Group 1 is often referred to as the alkali metal group, or simply the alkali metals. Again, hydrogen is usually not included, but it includes every other element in the column: lithium, sodium, potassium, and so on. Group 1 elements are very similar to each other in reactivity, meaning you can often remove one of these elements from a substance and replace it with another with very little change. What's also interesting about Group 1 is that the alkali metals react violently with water. What does that mean? Well, let's watch a video from Open University that shows what happens when very small amounts of alkali metals are combined with water.
Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame. The next element is rubidium. This time we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our fifth alkali metal.
So as you can see, alkali metals, whether it's lithium, sodium, or all the way down to cesium, react very violently with water. Francium wasn't shown in the video because most francium on Earth is very hard to find, very expensive, and dangerously radioactive. As a result of this, most of these alkali metals are usually not found in nature in their elemental form. Think about it. If sodium existed as an element in nature, as soon as it rained, we'd have a fireworks display. Instead, we usually find these elements as part of compounds. That's why you usually don't think of sodium as being a shiny metal. You think of it as being part of sodium chloride or table salt. These elements, while they have very similar chemical reactivities, change drastically when you bond them into compounds. We'll talk more about that later in the course. Next to Group 1 is Group 2. Group 2 are referred to as the alkaline earth metals, and they're also reactive with water, but not nearly as violently or to the same extent as those Group 1 alkali metals. Group 2 includes beryllium, magnesium, calcium, strontium, barium, and radium. And there's something interesting that happens here. Remember that because each of these elements is in the same group with each other, often you can replace one element with another, and this happens quite frequently in nature. Let's look at calcium. Calcium, as a metal, is shiny and has luster, it's conductive, and it's often solid at room temperature. This is probably not the calcium you picture when you hear the word calcium. Instead, you're probably picturing calcium either dissolved in milk or as something like the calcium that's present in your bones, or maybe calcium bicarbonate, baking soda, calcium carbonate, which is found in a lot of things including chalk. Even though calcium is a metal, it's often found in compounds, and one of the compounds that I just mentioned is the calcium that's in your bones. Right below calcium in group 2 is strontium. Your bones contain very small amounts of strontium that has replaced some of those calcium atoms. And this is what's interesting, is a very small amount of that very small amount of strontium is actually strontium-90. Strontium-90 is radioactive strontium that results from things like nuclear testing. In fact, there was basically an immeasurable amount of strontium-90 that existed in the world prior to nuclear testing in the 1950s. Because of this, anything that formed after the 1950s on Earth has a small amount of radioactive strontium-90 where you might otherwise expect calcium atoms to be. In fact, scientists have been able to use this when people try to pass off as real things that might have been produced hundreds of years ago. For instance, if someone wants to sell a Da Vinci painting and they argue that that Da Vinci work was original, scientists test for the presence of strontium-90 atoms, and if they find them, it means that it's a fraud, because strontium-90 didn't exist in any measurable amount prior to radioactive testing. This means that a very small amount of the atoms in your bones are actually radioactive atoms that resulted from radioactive testing throughout the world more than 50 years ago. So group 1 and group 2 are both interesting in terms of their reactivity. And there's two other groups on the periodic table that are interesting enough to have gotten common names, aside from just their group numbers. If we move over to the right side of the periodic table, we'll see group 7, which are called the halogens. The halogens include fluorine, chlorine, bromine, iodine, and astatine. The halogens, when they're in their elemental form, are always diatomic, meaning two atoms put together. So fluorine, when you see it in its elemental form, will always be two fluorine atoms, or F2. The same thing with all the other elements. Chlorine, in its elemental form, is Cl2. There's a couple interesting aspects to the halogens. For me, the first thing that's interesting about them is that they're actually extremely toxic. Each one of these in its elemental form could make you quite ill if you're exposed to too much of it. Chlorine, for instance, in its elemental form is Cl2, and that's actually a gas, chlorine gas. You may have heard of this because it's actually been used as a chemical warfare agent. It causes horrible burns as well as can damage people's lungs. It's the same gas that's released when people unknowingly mix certain cleaning supplies. Mixing an ammonia-based cleaning supply and a chlorine bleach cleaning supply releases Cl2 gas, creating again a very dangerous effect. As you can imagine, we don't run into a lot of these pure diatomic elements in nature. Instead, we often run into the halogens in forms of compounds, much like we saw with group 1 and group 2. In nature, the halogens are usually found as part of salt compounds, such as table salt, which is NaCl. In fact, this is where the term halogen comes from. It was originally halide, or salt. So group 7, the halogens, we usually experience them in a very non-toxic form as compounds such as table salt, but when they're pure, they can be very dangerous. You've actually smelled a little bit of these compounds anytime you've gone to a public swimming pool. Most swimming pools use chlorine as a disinfectant, and that very slight chlorine odor that you're detecting when you walk into a public swimming pool is actually an incredibly low concentration of chlorine gas. Of course, it's not enough to be dangerous to us, but it's a very light version of what happens in the more dangerous exposures. The last group on the periodic table that also has a name is Group 8, which is also called the noble gases. The noble gases, helium, neon, argon, krypton, xenon, and radon, are gases. And they got the term noble basically because these are the snobs of the periodic table. They're too good for everybody else. We'll notice that the noble gases are chemically inert, meaning if you take any one of these elements, helium for instance, and try to mix it up with other elements, it won't do anything. So whereas the group 1 elements are so eager to react that they explode when combined with water, you can mix helium with just about anything and nothing will happen. This actually makes them beneficial in settings where you want to avoid a reaction. If you're working with something that could have a spark and start a fire, working in an argon environment allows you to eliminate the oxygen that usually causes that fire reaction. Same thing if you're trying to avoid decay over time. Oxygen, which is around us in the air all the time, slowly chemically reacts with many different compounds. This is called oxidation, or more commonly rusting. By replacing that, often with something like argon gas, you're able to prevent those type of oxidation reactions. So the periodic table, even though it's complex, can be broken down into simpler parts.